Like, how much am I not going to take in the last 5 minutes?
So, shall we continue reviewing, or do you have questions? With both. And not exclusive, I guess.
Most of the stuff I was shaking on me covered yesterday.
Okay.
Like I was feeling a lot better about the second half of the course material than the first half.
All right. Any questions asked Ben?
Yeah.
I would love to do like a group final sometime. I mean, I think that would make so much sense.
I think it'd be fun.
Because that's like your work situation, right? It's not like go in this room, don't talk to anybody, solve this problem. So,
I really like that idea.
Yeah.
That'd be fun.
Yeah, but that encourages people to rely on other people.
that's the downside of it.
Welcome to the workforce.
Well, yeah.
Or you grade on input, you know.
Yeah.
Or do like a round robin where everybody has to say something.
Yeah. Yeah.
If you did a final like that and you included the entire class, you could lead that final in a way.
Yeah.
That's true. Yeah. You could call on people even.
Yeah.
Yeah.
I've been in classes where they call on people. It wasn't fun for me.
Well, I mean,
Yeah.
I don't think that would be the best solution, but
Yeah, but that's something I'd like to try to incorporate somewhere down the road.
Well, and you worry about relying on other people. Part of your grade could be how much you collaborate with the group.
Right.
Like
right.
your input is
You
even if you have all wrong ideas, at least if you're thinking the right way.
Yeah.
I think one of the big things to have.
It's an interesting idea.
Careful what you wish for.
Okay, maybe it sounds difficult, but honestly,
Yeah.
it sounds like a fun experience.
It does sound fun.
Yeah.
It does.
Another possibility for finals have a big programming one day.
Mm-hmm.
Split everyone into groups and do functions.
Yeah.
Kind of helps
it's not a bad idea.
helps simulate real world
Right.
experience because
Yeah,
that's
plus-
how it would be.
Writing specifications, following specifications, getting things put together.
2 hours,
Stuff like
everybody
that.
checks out a computer if they haven't done
Yeah.
one. Everybody contributes to the code base on that same day. That's
Yeah.
actually interesting.
There's a lot of room for creativity.
Because that would be way closer to what you're actually doing.
Yeah.
That would be far better too, because you can keep track of who made the changes.
Right.
So you would be able to tell who did what with the Git logs or whatever.
Yeah.
I had a professor for 224 a few years ago,
Mhm.
and she had us do a final project that was just like that.
Yeah, that's cool.
It's definitely harder to grade like that. So
It is.
But
It's fun. Unfortunately, a lot of assessment boils down to simplicity or definable metrics that are easily definable. I try to stay away from that as much as possible, but sometimes that's what comes out. All right, number theory. So, main themes for number theory: divisibility. A divides B means that B is a multiple of A, means that B can be written as A times some integer. Right? 3 is divisible by 1 because 3 is 1 times an integer. 3 is not divisible by 2 because 3 is not 2 times an integer. From that, we get a more general notion of modularity. So when we talk about modulo n, we're talking about remainders when you divide by n. Where we understand our remainder is bigger than or equal to 0 and less than n. So 7 modulo 3, we would write as 1 because 7 divides by 3 twice and you have a remainder of 1.
All in the context of integers.
All in the context of integers, yeah. All of this is good old integer land. Technically, 7 is also equal to a multiple of 3 plus 4. But when we look for modular equivalence, we try to stick to this. So 2 times 3 plus 1, that's a good value. You got a question?
Not anymore.
Okay, cool. And we saw a number of proofs related to these ideas. For example, if A divides B, then A divides 7 times B. And we can prove that directly by saying if A divides B, then B is equal to J times A for some integer J. And so we're trying to show that A divides 7B. Well, if we know that B is J times A, then 7B is just 7J times A. And 7A is an integer. So 7B is an integer times A, it's divisible by A. And in general, when we say two things are congruent modulo n, it means they both have the same remainder when you divide by n. So A is equal to J times n plus B, plus, right, so A is congruent to M. So A is a multiple of n plus whatever is congruent to, and B is also equal to some multiple of n plus that same remainder. And so A minus B is itself a multiple of m. And this is the other way to look at equivalence modulo n. Their difference is a multiple of n. And it's exactly the same as saying they both have the same remainder when you divide by n.
Did you start the camera?
Say again?
Did you start the camera?
I believe I did. Now I'm nervous. I gotta go double check.
We're gonna see on video, so I'm just like,
At least it's not funny. That's fun. So we talked about two shortcuts to exponentiation. One was modular exponentiation. So a to the b modulo n. And we observed that a to the 1 is congruent to a squared is congruent to a squared, a to the 4th is a squared squared, a to the 8th is a to the 4th squared. And so this is just a. We square this. If it's bigger than n, we reduce it modulo n. We square that to get a to the 4th. We reduce it modulo n. Each of these is going to be relatively small, meaning less than n, not equal to. And so we can find all the powers of 2 powers of a. And then if we want to find, for example, a to the 13th, that's a to the 8th times a to the 4th times a to the 1st. And so we can take these values that we found here and multiply them together. And it basically lets us do an exponent b of a number in basically log b steps, as opposed to b steps where we multiply a by itself b times. So if b is 1,000,000, we can do this in about 20 operations. That's much more efficient. So that's modular exponentiation.
When calculators evaluate large exponents, is this is the operation they're doing, or
No, they're probably just multiplying out.
really? Okay.
Yeah. Unless it's something esoteric that's doing extremely large exponents. The other form that we saw was if p is prime, and a and p have no common factors, which means a is not a multiple of p, then a to the p minus 1 is always congruent to 1 modulo p. If a is a multiple of p, then it's congruent to 0, and a to anything is going to be congruent to 0. So that's just making it an interesting case. And so if you want to compute, 5 to the 103rd modulo 101, that's very quick to do because we know from Fermat's Little theorem, 5 to the 100 is congruent to 1 modulo 101. And then you just have to multiply by 5 3 more times to get 5 to the 103rd. Prime numbers, we talked about the fundamental theorem of arithmetic, which is unique factorization. So you can write a number as a product of primes that's unique up to the arrangement of those factors. So 15 is 3 times 5 or 5 times 3, but you can't write it as any other product of primes. It doesn't happen to be 2 times 7, for example. We mentioned the prime number theorem, which is the density of primes. The number of primes less than or equal to x tends towards log of x as x gets ridiculously big. And that's just kind of a weird fact, and you can actually prove it with complex analysis, which is freaky in itself. Goldbach's conjecture, open question, can you write every even number as a sum of 2 primes? Twin primes, do you have an infinite number of pairs of primes that differ by 2? That's an open question. Greatest common divisors. We talked about Euclid's algorithm as a way of finding the greatest common divisor of 2 numbers. If the greatest common divisor is 1, we say they're relatively prime. So 15 and 8, the greatest divisor for both of those is 1. Neither of those is prime, but the largest number that divides them both is 1, so they're relatively prime. I mentioned the Chinese remainder theorem for solving systems of congruent equations, but we did not go into the details of that. And then some applications. So we talked about parity generation, which is modulo 2 addition of your 1s. We talked about hash functions, turning a string into a number and reducing it modulo the number of bins in your hash table. UPC codes, ISBNs, all of these things that let you do some sort of modular arithmetic on a series of digits to confirm whether that's a valid sequence of digits or not. So you can take a credit card number and tell whether it's valid or not by doing a certain operation, usually involving modular arithmetic on the digits and their positions. And we talked about cryptography. We talked about some simple ciphers, Caesar cipher, which is just a shift of your characters up or down. Transposition ciphers, which rearrange character positions in your string. These are easy to defeat with analysis of letter frequency and so on. And then we talked about public key cryptography. I won't ask you the details of that, okay? But the idea of a public key is that you have a different key for encrypting versus decrypting. So you can tell somebody how to encrypt without telling them how to decrypt. So everybody can use the same encryption code, but I'm the only one who can decrypt. And being able to encrypt doesn't give away the decryption key. And so that's where things like RSA come into play. And then we got to induction. So,
And everything changed.
and everything changed. There's more than bacon in dogs. Bacon, dogs, and induction.
Bacon dogs is the number 1. Going over and over again.
That's all that induction is. given that P of 1, P is some proposition, given that P of 1 is true, and given that if P of n is true, P of n plus 1 is true, for n bigger than or equal to 1, then we can conclude P of n is true for all n bigger than or equal to 1. That's all it is. And it comes up in so many different ways, as we've seen. But applying mathematical induction comes down to stating what your proposition is, stating your base case and showing or asserting that it's true, stating this inductive step, right, if Pn then Pn plus 1 is what needs to be shown, and then doing some work to show that that step is true. And then concluding, therefore, by mathematical induction, our proposition is true for all n. And the simplest example is climbing a ladder. If you're on rung n, you can get to rung n plus 1 by simply grabbing and pulling up. Right? Given that and the fact that you can get onto the first rung of the ladder, you can reach any rung of the ladder. Mathematical induction. So I will not ask you about odd pie fights or colors of horses, or subtle things like that. But we've seen lots of examples of this. We proved sums of series, sums of odd integers. We can prove that n is less than 2 to the n. Right, so we want to prove that that's true. Using induction, well, P of 1 says 1 is less than 2, and we know that's true because we know about 1 and 2. And then if n is less than 2 to the n, show that n plus 1 is less than 2 to the n plus 1. And the important thing here is don't write down what you're trying to show and start working with it. Right? We don't know that this is true. This is what we want to show is true. But we know that this is true. And so here we might do, and this one's not totally obvious. N is less than 2 to the n, so 2n is less than 2 times 2 to the n. And we know that because we're multiplying by 2. And so 2n is less than 2 to the n plus 1, because that's just 2 times 2 to the n. But we also know that 2n is n plus n. So n plus n is less than 2 to the n plus 1. And since n is bigger than or equal to 1, n plus 1 is less than or equal to n plus n, which is less than 2 to the n plus 1. And so we've got our inductive step, therefore n plus 1 is less than 2 to the n plus 1. And then we say we've got our base case, and given this, we can prove this. Therefore, by mathematical induction, 2 to the n is, or n is less than 2 to the n for all n bigger than or equal to 1.
You're right, that is not obvious.
That's not obvious, yeah. I got worried when I started if I was going to be able to do it.
Pretty cool one, man.
Cool. So here's some induction you can practice on. Show that. That one's even less obvious, I think. Generalized Morgan's theorem. So the intersection of n sets is the union of the complement of those same n sets. prove it inductively. 5 divides into the 5th minus n. That one's pretty easy to show using modulo arithmetic, but try to prove it with induction. Exponentiation of matrices with zeros off the diagonal. You can prove that with induction. Five divides 8 to the n minus 3 to the n. For n bigger than or equal to 0. Magnitude of the power set of S is equal to 2 to the number of elements in S, if S is finite. Some of these are a lot harder than what I'll ask you to do, but if you can do these and think about them, you should be in really good shape. Counting. I think that's what we did in counting: sum rule, product rule, combinations, permutations, and pigeonholes. So product rule, if you have multiple steps for a task, do this and then this and then this, the number of ways to do the task is the number of ways to do this step times the number of ways to do the second step times the number of ways to do the third. Sum rule is a task that can be done either like this or like this. Number of ways to do the process is the number of ways to do this task plus the number of ways to do this. So if you're ordering soup or salad, the number of ways you can order is the number of soups plus the number of salads. If you're ordering soup and salad, first you have to choose a soup, then you have to choose a salad. It's the number of ways, number of soups times the number of salads. And that really leads us to the notion of permutations and combinations. Permutation is ordered. Combinations are unordered. And we were actually doing those as soon as we started talking about product rule. So how many ways can you choose soup and salad, for example? And so there were formulas for these using factorials on top and bottom. Combinations also fall out of Pascal's triangle because they correspond to the number of ways we can get exponents of our first variable in a binomial. And I probably won't ask you weird questions about Pascal's triangle. And then pigeonhole principle, you have n objects and you have fewer than n boxes. You cannot place those objects in boxes so that there's only one object per box. If you've got more than n objects, you're going to have at least one box with at least two things in it. That's the basic pigeonhole principle. There's a generalized version that tells you the ceiling of n divided by m is the number of objects you'll have in at least one box. So we use that for a variety of things. How many people can you put in a room so that they have a unique first initial? And it's 26 because you can put them into boxes based on their first initial. 26 people, you can do one per box. 27, you can't. And questions with that, it's again a matter of taking what you've been given, trying to phrase it in some way that relates to containers and placing things in containers. and trying to take what you're trying to show and turn that into some statement about a container having more than one thing. That's a really crude general description of how you solve pigeonhole problems, but it'll at least get you started on it. And this led us in some way into recursion when we look at this idea of writing a function like that. To prove that this works, we make a proposition, fact n returns n factorial, for n bigger than or equal to 1. We can prove it's true for the base case by this statement, and the inductive step says if fact works for n minus 1, does it work for n? And that's exactly what this statement is saying. If we know that this is n minus 1 factorial, then this will return n times n minus 1 factorial, that's n factorial, so it also works for n. And then by induction, it works for all n bigger than or equal to 1. So there's this connection there between induction and recursion that we can use to verify algorithms like this. And we saw that with searching a binary tree, a binary search tree, traversing trees, all kinds of other things. And then we got into trees and graphs. And unless you have questions on trees and graphs. And then we got into languages. And here's what I want you to know. I want you to know those, because that's what we've been talking about for a few days. So these phrase structure grammars, that's the take-home I want you to have for what we've been talking about. So a vocabulary of symbols, a set of terminal symbols, a starting symbol, and a set of reduction rules. And either taking a grammar that you're given like this and being able to identify whether or not a string is a part of that language, or use this to produce one or more strings that belong to that language, or taking a description of a language and creating a grammar that generates that language, which usually means coming up with production rules. The study guide that I posted on Canvas also talks about the other parts that we've talked about or we might talk about this morning. Those will not be on there. Okay, if I ask you a question about grammars, it will be phrase structure grammars that we already talked about a few days ago.
So none of the brackets.
So no Bacchus-Nauer form BNF, no state machines, no Turing machines. Okay, even though they're listed on that study guide.
Can we use BNF instead of this description?
If you're really stuck and you do that, you might get some partial credit. But
You need to answer the
Can
question.
we get extra credit if we do both?
But there's always like fame and glory.
So we'll put that on our transcript and fame.
Yeah. And I'll be like, I had a student once.
Fame and glory, don't put 8 on the table.
Yeah.
I'm sure you would love to see fame and glory on a
Yeah,
transcript.
totally.
It starts with F. That means
Yeah, right. But it's got an A in the second word.
that's true.
So that averages out, right?
Yeah. All right, any other questions? Yeah.
So, some in the sum rule and product rule, that's kind of like when we have those kind of questions and it's, when you look at it, it's like it's obvious that you can do it. Like say, what was it? There was an example that we had where it's pretty much how many combinations per lock that has 9 unique things.
Yeah.
That would just be 9 times 9 times 9. How many things you have? That would be
Yeah, because to pick a combination for the lock is a sequence of tasks. You have to pick the first digit, and then the second, and then the third. And the number of ways to pick each of those is 9. And so the total way to pick a combination is 9 times 9 times 9.
And then-
And the combination and permutation is when, after you select one, you have one less.
Possibly not. Combination permutation more has to do with the ordering. So how many, if your combination, if the order didn't matter, right? So you've got 3 digits you have to recite to somebody before they'll give you access, right? So what are your 3 digits? And it doesn't matter what the order is, okay? That's a combination. And there's fewer of those than if the order matters. So this was one equation. This was basically the same equation divided by the number of ways to reorder things.
I'm trying to remember which homework it was that had a bunch of these, like homework 5.
Yeah.
It had like 10 or 15 questions all about this stuff.
Yeah.
Like, yeah, and I was reviewing those to look at it.
Okay.
So it was like the duck race problem,
Yeah.
that sort of stuff, yeah.
Yeah, and that's why I was like, that's the homework I was remembering. Is a lot of them like, look at the formula, it's like, I don't need to use this. I can just go 5 times 4 times 3 times 2 and I get the answer.
Yeah.
Or I could go through a complicated formula and get the exact same answer.
Right. And when you're doing 5 times 4 times 3 times 2, you're picking things, but your task has fewer choices each time. So you're
Yeah.
taking the cards out of a deck, for example. In the first one, you have 52 choices. The second one, you only have 51 choices, and so on. So those come up for both.
Yeah, I'm sure the formulas are useful as like the tasks get bigger and bigger,
Yeah.
you know.
What were the formulas? I
Um,
can find them, I know, but.
so that's permutations, and for combinations, you also divide up a number of ways you can arrange the things that you chose. I will now look at my notes discreetly and see if that's correct.
I think that's right.
Otherwise, I'll pretend to suddenly remember differently.
Well, this is discrete structures.
Yes, mine must be discrete. Okay, that looks correct.
The one on the right, permutation.
So this is permutations. Combinations. All right, we have 12 minutes to discuss the history of computing. Over the past 80 years. It's 15 years a minute.
15 years a minute, that's like scaled up like how many? Scaled down like
Yeah.
Oh,
So Alan Turing, how many people here saw the Imitation Game? Whoa.
and we call ourselves computer science.
Yeah.
Dude, we're college students.
Yes, I'm not gonna see
Oh,
the
Russ would probably
sensationalized version.
It was a cool movie, and it was actually like, I mean, it's very appealing to my geek, but it was actually like a really entertaining movie for people who aren't geeks also. So I have friends who like went with their non-geek friends, and everyone enjoyed it. It's a semi-accurate account of some of Alan Turing's work. So Alan Turing, we just had his 100th birthday a few years ago. He was a mathematician, and in the 30s he was studying questions of computability. And the question he was studying was, are there problems that cannot be solved? It's a nice, simple question, right?
For validated? No.
Yeah. And he needed to define what this means to be able to solve a problem or not able to solve a problem. So he was basically grappling with the concept of an algorithm. So can you describe a sequence of steps that you can use to solve a given problem? And there were no computers at the time. So this was pretty much a human concept, right? Describing and following an algorithm to solve a problem. So he needed a mechanism for defining more rigorously what this means. And he came up with a thing that we call a Turing machine. And it's a theoretical device that you could use to execute algorithms. Okay, this is 1930s. So a Turing machine,
Wait. That was theoretical in the 1930s?
that was theoretical. Well, it's theoretical for the following reason. A Turing machine looks like this. It has an infinitely long tape. And this tape can move back and forth. And there is some sort of read-write head sitting above this tape. So think magnetic or think ink and optics or something. And this head can do two things. One, it can read a single character directly underneath it on this tape. So it could be a set of digits, could be digits and letters, could just be 0 and 1. But you can have characters on this tape, and this can read what that current digit is, and it can also change what that digit is. So it can erase the one that's there and put a new one in its place. And the tape can move to the right or to the left. And that's all a Turing machine does. But it's got this infinitely long tape. And we define how it acts by describing what's called a state table. 250 Nightmares Return.
It can do operations too, right? I mean,
No.
it doesn't seem very useful to have something that can just read and write. That doesn't do anything.
That's all it does. It
determines-
reads, writes, and it moves the tape.
It has to be able to. do
But we have to
something.
be able to tell it what to do, when to read, when to write, what to write, which way to move.
Right.
And that's what a state table will do for us.
Can
Yeah,
it
pretty strong
store
tape.
what it reads?
It can write one character under the current spot on the tape.
Well, when it can remember what it
Nope.
read.
All it's got is the tape. The tape
30
is in
bits.
memory.
That's a pretty strong tape to be infinitely.
Yes.
And
And
then
never wears
uh,
out.
yeah.
So.
I mean, it's like so far ahead of its time. It's so weird.
So we have this state table, though. This is our program. It's a set of 5 tuples. Present state, character, next state, new character, and then how we want to move the tape. And we just list a whole sequence of these 5 tuples. And that describes how this machine works. So for example, S0, 0, S1, 1R, S0, 1, S1, 0R, S0, blank, S1, 0R, S1, 0, S2, 1 left, S1, 1, S1, 0 right, and S1 blank, S2 0 left. There's a program. And if you move to a state that doesn't exist, the machine halts. So I don't have a state S2 defined anywhere, so if this state fires or this state, the machine will halt afterwards.
Okay, so S0 is the state.
S0 is the state.
We check what the character is by reading it, and that's the
Yeah.
second argument.
Correct.
The next state is where we're going after this. We write a new character. You could write the same character and keep it the same.
Mm-hmm.
And
Left LR is left or right on the tape,
LR is left and right.
which is the pointer around.
more or less.
So does it just start with the first thing, or does it just start?
So
with
it starts wherever it starts. So in this case, this is our tape contents. It's blank over here, it's blank over here. We've got a 0, 0, 1, 1.
He is blank. Okay.
Okay, and I think I've written this with moving the head instead of moving the tape, because that's easier to do on paper. I'm just going to move the arrow around. So what does this do? It looks under the head. Okay, we start off in state 0. It looks under the head, it finds a 0. So we're going to go to state 1. This is going to change to a 1, and we're going to move to the right. So let me just do these in place. So now we're sitting like that, and we're in state 1. State 1, and we have a 0. It's going to go to state 2, it's going to change that 0 to a 1, and it's going to move to the left.
And then stop.
And state 2 doesn't exist, so it halts.
What? Boring.
That's boring. But guess what? Anything that you can do in Java or any other language you can do on a Turing machine.
Any other Turing?
Any other Turing compatible, Turing complete operation. This is a really powerful construct of computation. And it was really sort of one of the initial seeds that led to the creation of a stored program computer. And it's really not that bad to start writing programs on Turing machines. It looks really kind of archaic, but once you work with a few of these things, it starts to click, and you start to see things that you can do to do reasonable operations. So I'll post on Canvas, I don't have time to show it here, but there's some online simulations of this. And there's one I've got that you can load in a program to like multiply numbers. And it'll show you the whole program. It's like a few hundred steps, a few hundred states. And it'll go ahead and execute, and you can watch it move back and forth and change the numbers around. And you can run it at full speed or slow it down. And it'll count how many steps. And it's ridiculously inefficient, but it works. And it's kind of like writing production rules or writing BNF. It's quirky at first, but it's actually pretty workable once you get into it.
This is a strange concept to come out of the 30s. It's so
yeah.
surprising.
But he was exploring this question of can you, are there problems that you cannot solve? And the question that he went on to from this was what's called the halting problem. And the question is, given a program, can you tell whether that program will ever halt, will ever exit? It's a really simple question. It's a really difficult answer. If you could do this, you could change the world. For example, can you write a C program that tests Goldbach's conjecture?
Got it.
Right? I mean, you did that for your homework.
Boy, that would be.
So have it run until it finds an even number that can't be written as the sum of 2 primes and have it halt at that point. If you could hand that code to an analyzer and say, tell me whether this program halts or not, and it could come back in a finite amount of time and say yes or no, you got your answer to this conjecture. And there's a whole bunch of things like that.
Brute force conjectures that way.
Yeah. But, unfortunately, what Alan Turing showed is that you cannot solve the halting problem.
Thanks.
So there is no way to take a general program and tell whether or not it halts. And it's basically a form of a diagonalization argument, the same thing we did for trying to map integers to reals. You set it up, you throw in a little twist at the last minute, and you find a contradiction. For what it's worth, I don't believe that result, not completely. So I have a paper I've sent out to 2 different journals now, but I'm pushing to find a conference to present it at, that calls into question the unsolvability of the halting problem. Doesn't claim to know how to solve it, but I see an issue with the proof that it's unsolvable. So I may be like locked up in a rubber room, or I may be like publishing this sometime, who knows. But the general convention is that halting problem is unsolvable, and it's one of a long series of problems that are equivalent to the halting problem that are therefore also unsolvable. All right, let me leave you with a final punchline. I don't know if we'll get through this. But complexity of algorithms. So how long does it take to sort a list of n numbers if you do a good old bubble sort?
You told us this, I don't remember what you said.
Right off the top of my head.
Bubble sort, you have 2 nested for loops, right? Each loop goes through n iterations. Ballpark n squared, right? So we say order of n squared. That's a polynomial. It's a polynomial of degree 2. To search a binary search tree, log of n, that's less than n to the first. That's a polynomial.
A balanced binary.
It's a balance, yeah.
A balanced binary.
A balanced binary search tree, yeah. If it's unbalanced, it's order n. So lots of problems can be solved in what's called polynomial time. It may be n to the 10,000th, It may be some horrible growth rate, but if we can find a polynomial with some finite degree that bounds how much time an algorithm takes, we say it's solvable in poly time. What it technically means is solvable in polynomial time on a Turing machine. In particular, on what's called a deterministic Turing machine, which is what I just described. But there's an even more theoretical version of a Turing machine called a non-deterministic Turing machine. A non-deterministic Turing machine is a machine with a genie built in. It's a machine that has a genie that knows which way to resolve conditions in order to get you to a solution. So here's an example, traveling salesperson problem. We want to find the shortest path that lets us visit a set of cities. We could go through and we could simply try every possible path, right? That takes n factorial, it's not polynomial anymore. But if you tell me, here's a path, and this is the shortest path possible,
Oh, this.
right? I can take another path, and in polynomial time, actually in n steps, I can tell you whether another path is shorter. So if I knew which way to try to take me through my shortest path, I could do that in polynomial time. So a non-deterministic Turing machine has better performance. The question is, for something like traveling salesperson, that's solvable in polynomial time on a non-deterministic machine, but we don't know what it's solvable in on a regular deterministic machine. We know it's solvable in n factorial, but is it better? So we can break problems into classes. Class P is solvable in polynomial time. Class NP is solvable in polynomial time on this magic machine with a genie inside. TS sits inside here. The question is, does it also sit inside here? Can we find a polynomial algorithm? And there are questions called NP hard, which are so difficult that if we can find one of these problems to be class P, then all NP hard problems are class P. And TS is one of these NP hard problems. So if anybody can find one algorithm for solving TS in polynomial time, there's a whole list of problems that are suddenly solvable in polynomial time, including things that break cryptography and make our life easier and also more hectic. So
find that.
So if you find that, yeah, and there's a fairly bad Amazon movie called Traveling Salesperson, or P equals NP, I think is the name of the movie, that explores that.
I think it's just called NP.
Just called NP? Okay. It's not great, but it's interesting. So that's a popular area of study for people, is like, can we find this? And it's considered to be extremely difficult. It's not impossible to answer that question, but it's still technically an open question.
It is traveling salesperson.
Okay, so there's your last non-graded homework. Find a polynomial solution to TS and get yourself real fame and glory.
Or a lifetime subscription to something run by no
Yes,
such agency.
right.
Ungraded
Yeah,
is
special
what I call
accommodations
more
and
that
more
fame and
fun.
glory you mentioned earlier.
All right, that's our course. Thank you so much. It's been fun and interesting for me. Hopefully you got some stuff out of this that'll help you. It will definitely help you in 222. Even if we never actually do this particular stuff again, it's going to be in there working in a lot of what you do with data structures and other things in computer science. So that's good. All right, I will see you next time.